Second speaker today is Lydia Liu. Lydia is a third-year PhD student in the computer science department, advised by Moritz Hart and Michael Jordan. And her research interests are to establish the theoretical foundations of machine learning algorithms to have reliable performance. Today she's going to talk about competing bandits in matching markets. Over to you.
Thank you. Thank you everyone for coming out today. I will be talking about joint work with our previous speaker, Haria, and also our advisor, Mike Jordan. So today I'll be talking a lot about matching markets. So if we think about matching markets, we actually know many examples of these already. You have two sides of the markets that must be matched, like say residence to hospital. The hospitals have certain constraints. Each resident can only go to one hospital, so both sides have constraints on their capacity, and they also have preferences for both sides. So residents might prefer certain hospitals, and hospitals have a ranking over residents. And we also see this with like a school choice, matching students with high schools, or even matching jobs with job candidates. And there has been a very long line of work since the 60s looking at these two-sided markets and how you can achieve efficient outcomes for these markets. But today we're more interested on a modern twist on this problem, which is to think about a problem that that fits matching markets that we see more and more of today, which is markets that are facilitated by online platforms with massive numbers of participants on both sides, and these participants interact with each other repeatedly. So we're interested in capturing this kind of the structure in a different kind of problem. So just to illustrate what I mean by a matching market, let's think of a simple example here. You have job candidates on one side and employers on the other. The job candidates have certain preference orderings over the employers, and the employers have certain preference orderings over the job candidates. And if we already had these full preferences, then now a desirable solution concept is to find a stable matching. And that means that in this matching, no two participants would prefer to be matched with each other over their assigned matches. And in this case, there's one unique stable matching, which looks like this. We want to find a stable matching because when we have a stable matching, then there's no incentive to deviate for any pairs of players. So we can say like the market has reached an equilibrium in that sense. So now in the 60s, Gale-Shapley came up with the classical deferred acceptance algorithm that always outputs a stable matching for any preferences, any set of preferences that you submit to them. And in this algorithm, one side would just iteratively make proposals to the other side in order of their preferences. The other side will accept also only if the proposal is better than the current proposal that they have. So it's a very simple algorithm, but it's guaranteed to always output a stable matching. And in particular, this matching will be, out of all the stable matchings, it will be optimal for the proposing side and Pessimal for the other side. So there's this nice structure here when you apply the Gale-Shapley algorithm. But we're interested in a different setting. So to run Gale-Shapley, you have to give Gale-Shapley, you have to give the algorithm the preferences for both sides of the market. So those have to be known. But what if these preferences are not known a priori? And instead, the market participants can only observe noisy utilities for those matches by interacting with the other side of the market. So let's say they don't know their preferences. Say like in an example we can think of is in online labor markets, I might have a job that I need someone to do, but I don't know if they're the best person for the job until I've seen them do the job, for example. And because these kinds of feedback are stochastic, you might have to you might have to try out an option multiple times to get a good confidence over my own preferences. If I have a customer, I'm going to a bunch of restaurants, maybe going just once is not enough. Maybe I have to go multiple times. And I will be caught in a dilemma to whether to try a new restaurant or to go to a restaurant that I seem to have gotten a good signal from before. So now you're starting to see that in this case where we have uncertain preferences, there is the emergence of an exploration-exploitation trade-off. And to think about this trade-off, we go back to the classical multi-armed bandit problem, where you have one agent who's trying to play different arms. Let's say 3 arms here. And whenever you pull an arm, you get a reward that's drawn randomly from the reward distribution for that arm. So the rewards are random. And we assume that they're sub-Gaussian, so the reward distributions don't have crazy tails. But a priori, we do not know which is the best arm. So we're hoping that as we try out different arms, we're doing this in a clever way such that on average, we're doing almost as well as if we had known what is the best arm to begin with, right? And this is captured by the notion of regret. So n is the horizon number of steps that I get to pull the arms, k the number of arms, x sub I t is the reward of arm I at time t, and h sub t is the sequence of arms that I've chosen over this time frame. And just to recap, regret is the difference between 2 terms. The first term is the total reward of the best arm. So I'm maximizing the expected reward over the set of arms that I have. And the second term is the reward that I obtained from the action sequence that I actually chose. I want to minimize the difference between these 2 terms because I want the sequence of actions that I took to be in expectation as close as possible to the total reward of that best arm. Right? And the goal is to have methods that achieve sublinear regret. And here sublinear means sublinear in n, the horizon number. So what that means is that if I divide this expected regret by n, then if my regret is sublinear, then this thing will go to 0 as my horizon goes to infinity. So one simple heuristic that actually achieves the optimal regret guarantee is this upper confidence bound method, which many of you might already be familiar with. So I'll just quickly recap that. In this method, at every round, I will look at my past data, and I'll construct confidence intervals based on those rewards around the means of all my arms, right? And then I will pick the arm that has the highest upper confidence bound. So in this case, I'll pick this arm that has the highest upper end of the confidence interval. And then I'll get a reward from this and update the UCB accordingly. And then now maybe I'll sample some other arm. And this simple heuristic has the optimal regret guarantee. So let's say arm 1 has the highest mean reward. So we denote the reward gap for all the other arms as delta sub I. So that's the suboptimality of all of the other arms relative to arm 1. And the regret of UCB is logarithmic in the horizon. So that means that actually my regret is growing very, very slowly over time. And also there's a dependence on the gap sizes, on the inverse gaps. Meaning if the gaps between certain arms are small, if I have trouble distinguishing between pairs of arms, distinguishing between the best arm and some other arm, then actually that also increases my regret. So this is the optimal dependence on the horizon here. And I will talk about the result will be useful later. So I just wanted to keep that in mind. So let's go back to our problem setting where now we want to introduce a competing player to the multi-arm bandits problem. And we want to introduce a BAIR. And this BAIR might have different reward distributions from the human for different arms. So let's just say those blue curves are the reward distributions for the BAIR. And if they pick the different arms, then they all get rewards from their respective reward distributions. But if they pick the same arm now, what do you think will happen? Right, so if they pick the same arm and each arm only has a capacity of 1, so actually only in this setting, they might be competing. So actually, the more competent player, or the more, in this case, the more go Bears. So the BAIR wins the conflict and gets the reward. Yeah. Yes, we don't want the other school to get the reward. So yeah, so here we're seeing this part where there is competition, where if 2 players pick the same arm, the arm might prefer one of the players more, so the most preferred player gets a reward. So just to summarize what is the problem setting here, we have a setting where there are players on one side and arms on the other side, and the players get noisy rewards when they pull the arms, but the same arm can have different mean rewards for different players. So this models the fact that the players can have different preferences over different arms. And then the arms have known preferences over the players. So just for simplicity's sake, let's say we can also consider the case where the arms have noisy preferences over the players, but let's just say the arms have known preferences for now, players get noisy rewards. And then when multiple players pull the same arm, only the most preferred player gets a reward. At this point, I'll mention some related work as well in the literature. There has been a lot of great work studying multiplayer bandits with this type of collision, but the assumptions is crucially different because most of these work will assume that when two players choose the same arm, no one gets a reward. So there's like a different setting here, and we focus on the competition setting. And there's some other work also looking at matching in like an online setting, but with different assumptions. Yes?
So is the motivation for the competition setting that I should implicitly be assuming there's some other party on the other side of the market that's making decisions and picking who they prefer?
So in this case, the arm is picking.
Right.
Yeah, the arm is picking.
We think of the arm as like the other side of the market.
Yes, exactly. Yes. So what is the right notion of regret in this matching market? So we have like players on one side, arms on the other side. So if the players knew their regret, right? So we want to know what if the players knew their preferences, then they should always choose their stable match. And the intuition behind this is if I always pick something better than my stable match, then at some point the other players, assuming that they're also playing optimally, someone's going to kick me off that arm because that arm is not my stable matching, right? There is like a other player, and the arm, both the player and some other player and the arm are incentivized to pair with each other instead of the player pairing with the arm that's too good for that player in some sense. So the bar here that each player should be comparing their rewards to is actually the stable match, right? In this case, if there is a unique stable matching. So just to write this out formally, if let's denote the stable arm of each player as M of I. So for player I, M of I is the stable arm, and then M sub T is just a matching that is played at time T by all the players, right? So it tells me for each player what is the arm that they pulled successfully. And then mu sub I of J is the mean reward of arm J for player I. And then the stable regret is just a difference between two terms again. Now it's the first term is the mean reward, not of like the best arm for that player, but the stable match for that player. And then again, I want to minimize the difference between the reward that the player achieve over a sequence of matchings versus the mean reward of the stable match. So if there are multiple stable matchings, then we need to take a bit more care because this is no longer well defined. So instead, we can define two notions of stable regret. One is where we compare to the worst stable match out of all possible stable matchings, and the other is you compare to the best stable arm out of all stable matchings. Yeah.
So in principle, a policy could change by not doing a stable matching, but achieving high reward, right?
Oh yeah, you don't have the M sub T doesn't have to be stable every round. What do you mean? Is that what you're asking?
If you're not constraining to be stable, then like, in principle, I could find the assignment that maximizes the right hand side and keep playing it.
Sure.
That would achieve negative regret, and that's some
Yes. So the regret can in general be negative.
No, I
Yeah.
understand that.
Yeah.
But
So you're saying that this having a low stable regret doesn't guarantee that the matching you're playing is always stable, right?
Exactly.
That I agree with you. Yeah, that I agree with you. But we want some way of quantifying like how well is each player doing with respect to what they would have gotten if everybody knew their preferences to begin with. Yeah. So we want to quantify what is the burden of learning in that market setting. So yeah, the algorithmic question we're asking here is actually how do we achieve a sequence of matchings that has low stable regrets for all the players, low stable regret for all the players, and yeah. So one simple algorithm involves this matching platform that is allowed to communicate with all players. So every round we just have the players rank their arms by the UCB of each arm's mean reward for themselves. So different from the classical setting, you just don't just like pick the UCB. You don't just pick the arm with the high UCB. You actually rank all the arms. And then now you submit these rankings to the platform, which will run Gale-Shapley algorithm, or actually any algorithm that outputs a stable matching would be fine here to match the players and arms according to the known preferences of the arms and the UCB-based preferences of the players. And then after the players, after you get that matching, the players receive rewards from those matched arms, and they update their UCB for the arm. So here's an informal theorem on the regret guarantee. So if there are n players and k arms in the market, and you run this algorithm, we can guarantee that the Pessimal stable regret of player I satisfies this upper bound. So if you look at this upper bound, this regret is growing with the market size, with n and k. But it's nice that it's logarithmic in the horizon number. So it is rate optimal for the horizon, which is good, meaning that this is growing very slowly with time. But now we have a much worse dependence on the gaps of the arms rewards. So this depends on 1 over the gap squared, where the gap here that is important is actually the minimum gap of all arms rewards for all players. So notice that this gap is not just the gap that is experienced by player I, it's actually the worst gap in the whole market. And this is, of course, a worst case bound, but that is to say that we can find some set of preferences where if one player has to explore more, there may be externalities on other players in the market. And you can see this effect in a very simple example. So let's just have a market with 2 players and 2 arms. Say player 1 prefers arm 1, player 2 prefers arm 2, and both the arms prefer player 1. The unique stable matching is this one. But in order for player 2 to be matched with their stable arm, player 1 must first correctly decide that they prefer arm 1 over arm 2, right? And statistically, this will require 1 over gap 1 squared rounds of exploration, right? So every time player 1 is exploring, ranks arm 2 over arm 1, for example, then player 2 will have to play arm 1. And those times, player 2 will suffer a gap of gap 2. And this gap 2 can be very large. It doesn't have to be related to gap 1 at all. So this the dependence of player 2's regret, stable regret, on 1 over gap 1 squared is actually correct here, right? So we just showed that this is a tight dependence. And if you ran simulations, you can also see that if you had a very small gap player agent, player 2's regret is just very big for very small gaps, but agent 1's regret is actually very small for small gaps. Because if all the arms are, if the arms have the same reward, then player 1 never has any regret, right? So another interesting question now here is incentive compatibility, right? Because you have a market, and you're asking these players to submit their rankings to you, but do they have the incentive to report those rankings honestly, in some sense? So the question we ask here is this question. So if all the other players are submitting their UCB preferences and the platform is running Gale-Shapley, and how much can a single player improve their stable regret by submitting something maybe a bit more clever? Can they gain much from this? And it turns out that they might not be able to gain much. No, it turns out that they cannot gain much. So if you look at their stable regret, we can actually lower bound their stable regret. So it's saying, let's just ignore this optimal here and assume that there is one unique stable matching. And here, this lower bound is saying that you could potentially do better than your stable matching, but your the amount of quantitative gain you have over this reward of your stable match is only of order log n. So on average, the amount that I'm beating my stable arm is going to 0 very quickly. And so the intuition here is that even if I try to do something clever or submit some other preferences, I can only do better than my optimal stable arm if other players are making random ranking mistakes, because I am running this GS algorithm. So if they made ranking mistakes, but they're running UCB, they cannot make ranking mistakes very often. So that's why you can lower bound the regret of any one player that is deviating. Yes?
What if the other players are not submitting their UCB?
Sorry?
What if the other players are not submitting their UCB?
Yeah, then I think in that case, it's hard to, so all bets are off. And it's also, I guess, then the question is like, what do we mean by, like, you mean by like, are they colluding or something?
Right, exactly. I'm trying to imagine.
Yeah.
Players decide to collude and
Yeah.
submit.
Actually, in that case, I think you can still get some kind of result in that case. Yeah. Some kind of result on the limits to a group colluding. The group has limited gains. Yeah. But yeah. So just a simulation here again to show that this lower bound is actually tight. So if we ran this for a very simple setting where you have like a global ranking of players and a global ranking of arms. And it turns out that the worst arm actually has 0 regret. Because the worst arm, no matter what the worst arm gets, is going to be better than their stable arm, which is whatever the worst player gets is going to be better than their stable arm. So in this case, the worst player is very happy because when uncertainty can only help them. Because if everyone was certain, then they'll always get the worst arm, but now because there's this uncertainty, the worst agents are actually benefiting from that. Whereas the best players are the ones who have positive regret. So to summarize, we studied this multiplayer bandit problem in a matching market setting, and we looked at this notion of stable regret. And the algorithm that we proposed here actually has a good stable regret guarantee. But that is player Pessimal. So there's an interesting fact that why this is actually player Pessimal, but I don't have time to really talk about it. Happy to talk more offline. But it's player Pessimal precisely because the uncertainty in the preferences actually has certain properties that make it hard to achieve the player optimal stable regret if we just did GS-UCB. So there are many open problems here, whether we can achieve player optimal stable regret, and also like the question Sami asked just now, what kind of other things can we say about the limits to strategic manipulation? So with that, I will close the talk, and thank you. Happy to take questions.
Any questions yet?
So do you mind going back to your results?
Which one?
The slide that you just showed. That'd be, okay then. Sure. Yeah. The slide with the figures.
Figures. This one?
No. Right at the end, the results.
Oh, you mean the plot?
The plot, yeah.
Right.
So in this example, it seems like the total regret is actually negative.
Oh no, I'm just showing like 5 out of the 20 agents. So,
Oh, okay, all
yeah.
right. Okay. So can you
But
get
the total regret can, in general, be. I mean, there's no such concept as total regret.
Right, no, I understand. But like, can you guarantee that the matching that you eventually converge to, in some sense, is going to be stable? Is that so? Like, as the policy proceeds through the rounds, the matching for large n is going to be somewhat stable.
Yeah. So the thing is, when you're running UCB, even as time goes to infinity, there will be some times when you are going to explore.
Right.
So we can guarantee it in this quantitative sense.
Right.
But not in you will always be stable forever kind of sense.
Okay, right.
Yeah.
But like, when n is large and you say you play 100 times and 90 times or for a large number of times, most of them will be stable or some notion like that.
Yeah, you could possibly get something like that from the stable regret guarantee. Yeah, it's possible.
Any other questions for the speaker? If not, let's thank Lydia and Horia once more time. Yeah.